Now we're ready to actually find the solutions to one of these second-order homogeneous linear differential equations with constant coefficients. Meaning a problem looks like this, now we can actually find the solution. To start, let's think on a very basic level about what kind of solution we should have. In other words, what kind of function y, when you take itself, its first derivative, and its second derivative, and then you multiply them all by constants and add them together, can you get 0? Now let me be more specific. If we have this function, and its derivative and second derivative are going to all add up to 0, that means that when you take the derivative and then take the second derivative, you need to end up with the same kind of function. In other words, if y was the sine function, y prime would be cosine, y double prime would be, again, involving sine, and then when you add them all together, the two sines could cancel, but the cosine would have nothing to cancel with. So, when you take the first derivative and second derivative, you need to have the same structure to it, because they all have to add up to 0. If they didn't, then we would have to deal with more complicated situations. But for now, if they're all adding up to 0, that first derivative and second derivative have to have the same form, again because they're just being multiplied by constants. And so nothing is changing the structure of the function, just the coefficients. So what function do we know that when we take its derivative and its second derivative and so on, we end up with the same form to the function? It doesn't really change the structure. And the easiest answer is the exponential function. So we're going to assume that our solutions y, both of them, y1 and y2, equal the exponential function, specifically e to the rt. So for different values of r, we would get different solutions, and that's all that's going to change. y1 and y2 will simply have different values of r that are valid here. And now to plug things into that equation, we need to find y prime, which would be r e to the rt, and y double prime would be r squared e to the rt, which we can substitute in, and we get a r squared e to the rt plus b r e to the rt plus c e to the rt equals 0. And if we can find what r has to equal, given values of a, b, and c, then we'll be done. And again, as I pointed out, we have two solutions here, y1 and y2, so we can expect that when we solve this, we'll have two answers for r that both work with this equation, and one of them will generate y1 and the other one will generate y2, and they'll both have this form. At least at first, although things will get slightly more complicated later on. So if we look to solve this equation, we notice that there's an e to the rt that's common to all terms, so we can factor that out. And then if we're solving an equation, and we end up in a situation where we have two things multiplied together and equaling 0, we know that either the first part must equal 0 or the second part must equal 0. But it turns out that this exponential function will never equal 0. No matter what value of r you select, you can never get that to equal 0. Which simplifies things for us, because we have something that can't equal 0 times ar squared plus br plus c, and that equals 0, so we know that ar squared plus br plus c must equal 0. Based on this relatively straightforward assumption that our solutions have this exponential form, we pretty quickly get to this conclusion, that the value of r depends on the solution to this quadratic equation. Notice that we've taken this differential equation, which looks complicated, and we've boiled the question down to an algebra question. We really just need to be able to solve a quadratic equation like this. This is what's called the characteristic equation. Meaning for the second order differential equation shown at the top here, we can immediately, in a given problem, write down the characteristic equation that will tell us the value of r once we solve it. So we can immediately transition into a algebra problem, and then when we solve this, which we know how to do, then we'll have our answers for y1 and y2. Notice how we do this to make this jump more easily. From a times y double prime plus b times y prime plus c times y equals 0, we get a r squared plus br plus c equals 0. So notice that the second derivative gets replaced with r to the second power. The first derivative gets replaced with r to the first power. And even the function itself, which you can kind of think of as the 0th derivative, gets replaced with r to the 0 power, which is why there's nothing here. It's like a 1 in that place. But if you just remember that y double prime becomes r squared, y prime becomes r, and y becomes 1, then you can immediately write down the characteristic equation. But you should understand where this comes from. It isn't a magical equation that pops out of nowhere. It's based on a relatively straightforward assumption, and then a little bit of algebra work where we plug it in and derive this characteristic equation. So to solve this, all we need to be able to do is solve a quadratic equation. If we can, we'll solve it by factoring, because that's usually the quickest and easiest way to do it. But if we ever get stuck, we can always use the quadratic formula. So r would be the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Just as a reminder, in case it's been a little while, but we can always fall back on this quadratic formula. If we can, though, we will factor this characteristic equation to solve for r. And again, when we do, we know to expect two solutions for r, generally. We'll talk about that more in a second. But those two solutions for r will each give us a solution for y. So that's where we get y1 and y2. And then if you remember, the full solution at the end is going to be c1 times y1 plus c2 times y2. Okay, so when we start solving a quadratic equation, we need to think through what our solutions can look like. Because I mentioned that generally you'll expect two values of r, and if you get two values of r, then those two give you your two answers, y1 and y2. That's the simplest case, and that's the one we're most familiar with. But there are other possibilities for what you can wind up with as the solution to a quadratic equation. So we'll just review real quick and remind ourselves of what kinds of solutions we can get, because that's going to slightly change how our answers look at the end. Let me show you what I mean. So the first possible case, that's the easiest one, is when you get two distinct real answers for r. So something like r equals 3 and negative 4, for instance. In that case, your solutions would be y1 equals e to the 3t and y2 equals e to the negative 4t. Or you could swap the labels. It's not really important. But in general, we would have y1 equals e to the rt using one of the values of r, and y2 would have the same form with the other value of r. So that's the simplest case, and again, the one you're probably most familiar with. Now let's think for a second about where these solutions come from, looking at this quadratic formula. If you remember, you learned this back in your pre-calculus course most likely, but if you remember, this is all based off of this square root here. And that's what's called the determinant of this quadratic formula, because it determines what type of solutions you get. If that square root is a positive number, then that means you're going to have something plus or minus, and that plus gives you one answer, the minus gives you the other, and everything's real numbers, and that corresponds to a parabola that intersects the x-axis twice. So that's the, again, most familiar form, and it's if the determinant b squared minus 4ac is positive. We're not going to really worry about checking that before we solve. We're just going to solve and see what our answers look like. But if you want to tie it back to what you're familiar with from pre-calculus and so on, that's what that looks like. The next case is when you get a single answer for r, but it's a real number. And that's the case where if you graphed it, the parabola would touch the x-axis at one point and one point only. This is the case where the determinant equals 0, and so you don't have anything being added and subtracted, so there's only one answer for r. In that case, this is where we need to think back to the concept of linearly independent solutions. Because if we said y1 equals e to the rt and y2 equals e to the rt, those two solutions are not linearly independent. One is a constant multiple of the other in a trivial sense because they are identical. So we can't have the two solutions be the same because that breaks that concept of linearly independent. Now, I'm just going to show you what we do to get around this without going into a lot of background and proving it, but you can actually prove this relatively simply just by substituting in and checking that it works as a solution. But it turns out that for one of these solutions, we just multiply by t. So we have e to the rt and t times e to the rt. Again, we're not going to take the time to talk about why that's true, but very simply you could take that and substitute it in and check that it works, and it does. So as I mentioned, with linearly independent solutions, there's one case where we need to be aware of that, and that's this case here, where we have a single value for r. We need a special solution for y2, that's t times e to the rt. The last possible solution, we've already seen where this determinant is positive or 0. What if it's negative? If it's negative, you'll have a square root of a negative number, meaning you'll introduce complex solutions, where you have a real part and an imaginary part. And so we can have two complex roots, and again with a real part and an imaginary part, this looks like the situation where if you graph it, the parabola does not intersect the x-axis. So complex solutions in general don't show up on the kind of graphs you're used to drawing, but they are certainly useful and often arise in applications as well. If you're dealing with vibrations or circuits like we talked about with applications of second order equations, these complex solutions come up a lot. So a complex root in general is going to have a real part, which I'm labeling with alpha here, plus or minus a imaginary part, which I'm labeling with beta times I. So alpha and beta, just the first two Greek letters. Think of them like A and B, but we've already used A and B to mean something else with these problems, so I used alpha and beta here. Don't get mixed up with the notation. It's just a real number plus an imaginary number with a real coefficient. So alpha and beta are the two coefficients here. For example, we might have something like 3 plus or minus 2i, something like that. So for the solutions here, you might say, okay, we have two complex roots, so let's let y1 equal e to the alpha plus beta I, and let's let y2 equal e to the alpha minus beta I. The problem with that is now we're dealing with complex numbers in an exponent, so things get really nasty and unfamiliar. So rather than doing that, we're going to write a different looking solution, And again, I'm skipping over some of the development of this just for the sake of time, but if you're interested, you can learn more about this on your own time of how we get from these solutions to the ones I'm about to write down using Euler's formula. But it turns out what we write is y1 equals e to the alpha t times cosine of beta t, and y2 equals e to the alpha t sine of beta t. So all that means is you take the values for alpha and beta. Remember that alpha is the real number by itself, beta is the coefficient of I, and just replace alpha and beta in these formulas and you're pretty much done. So again, we're skipping a little bit of the development, we're leaving it unsaid, but for now we'll just take these solutions as they are. So those are the two solutions, y1 and y2, if you have complex roots in your answer for R.